We're going to talk about gravity. If someone asked you what gravity was, most of you would have some kind of definition. What would you say? What would be your personal definition of gravity? Not what the books say, but what you say. Holds you down? Okay, holds you down. Does anyone have any other ideas of what gravity is besides holds you down? That's it? Basically, everyone agrees. That's what our definition would be. Holds you down. Stacy? Something hard? Hard. What do you mean by hard? You can't push it down? Okay, very strong maybe instead of hard? Okay, the gravity that we feel on Earth is very strong. It does hold us to the Earth, okay. Gravity exists a lot of other places. Does gravity exist on the moon? No, we don't know. No, because we'd be floating around, huh? Because if you didn't, you'd be floating around. You float around on the moon? When they landed that spaceship there, once they landed, sometimes it kind of floats off, or does it stay put? It ain't no gravity in some of them places. There's less gravity, but yes, there is gravity. There's not as strong a pull. Now, why not? It's the atmosphere. Nope, the atmosphere doesn't have anything to do with it. What's another difference between the moon and the Earth besides atmosphere? Size? Size, exactly. Now, which one's bigger? The Earth? So that the Earth has more pull because it's bigger. So if you get something that's even bigger than the Earth, it's going to have more pull. Remember the cans? When you picked up the can of pop, here's what it weighed on Earth. And when you tried to pick up the one that was on Jupiter, remember how heavy it was? Jupiter is much larger with much more pull of gravity. A scientific definition of gravity is the attraction between two objects, any two objects. Not just one big object and one little object like a person, but any object. And so when you say, I'm attracted to so-and-so, you really mean it, because there's a gravitational pull between any two objects. You are an object, and if the object of your affection is an object, then there's a gravitational pull between you. And it can actually be measured. It is very, very small. Otherwise, you go crash, slamming up against them all the time. But it would be really hard to walk, bumping into all these things and people all the time. But there is a gravitational attraction. Now, we talked about that before, about how you are pulled toward the center of the Earth. But remember that you are also pulling up on the Earth. The Earth is pulling down on you, and you are pulling up on the Earth. Now, why can I say that? Which one of Newton's laws says that I can say that? The third one. The third one, which is the one that says what? For every action, there is an opposite reaction. So the action, Earth pulls down on you. The reaction, you pull up on the Earth. Well, you're so small and the Earth is so big that you don't drag the Earth around with you. And it's also when you think about all the different people covering all of the Earth, and they're all pulling it in different directions, it pretty much stays right where it is. Now, I don't know if all people in the whole wide world, all the animals and everything in the Earth, and all of the everything run around and stand in the United States, if we could pull the Earth, but I still think we would be so small of mass compared to the Earth that it probably wouldn't make much of a difference. Okay, so mass is one thing that has to do with gravity. What about the sun? Now, the sun is much, much larger than we are, and if we were to stand on the sun and not get burned up, the gravitational pull would be even more than it is on Jupiter. So why doesn't the Earth go flying into the sun? What about the sun and the Earth and the moon? The sun is a lot larger, but it is also what? It is closest to the moon. Hot? Yes. It's a lot further? It's a lot further, right. So gravity depends upon size and distance. So both of those come into play. So the sun, since the sun is a lot further away from us, the gravitational pull is just enough to keep us in orbit. We're actually falling into the sun. We are actually doing this all the time. It's just that as we fall into the sun, we are so far away that we miss, and we fall away, and we miss again, and we keep missing, actually falling into the sun. That's all an orbit really is. So we are actually falling into the sun. But because we're so far away, we don't fall in and burn up. We fall and miss and fall and miss and fall and miss. We kind of fall around the sun. With mass, what did we decide about forces? Because gravity is a force, if we double the mass, what happens to the force? To keep it at the same acceleration, what? We need more, right? How much more? If I double the mass, would I need twice as much? 3 times as much? 4 times as much? Twice, right? Twice the mass, twice the force. So if Earth is twice as big as the moon, Earth would have twice the gravitational pull. That's pretty obvious because that follows Newton's the second law. The problem with distance is that distance goes in quarters. Twice the distance, 1/4 the gravitational pull. So mass is what? Twice the mass, twice the force. But with distance, twice the distance, 4 times less gravity or 4 times more gravity. So if you're 4 times as close to something, you have 4 times the gravitational pull. So but if you're twice as far away, it would have 4 times less gravitational pull. That's why the orbit of the Earth may be affected by other stars in the sky, but considering the closest one is 4.5 light years away, it doesn't really have a profound effect. Because if it were twice the distance of our sun, you would only have 1/4 the gravitational pull. So it's many thousands of times the distance of our sun. And so the gravitational pull is very minute. So all of this idea that if you were born under the sign of Taurus, which has to do with the constellation, or if you were born under the sign of Aries, which is the one that's going on right now. Anyone have a birthday in the near future? When's your birthday? Thursday, April 2nd? All right. Or if you were born under the sign of Leo, the idea that something so distant could put enough gravitational pull on the Earth to actually influence you for your whole entire life is a little bit strange. Okay, I mean, it's fun to talk about, but I wouldn't put a whole lot of stock into it. I don't think I've planned my whole life around what my horoscope said. On the other hand, when you get something that's very close, like the moon actually does put a gravitational effect on the Earth. And it's one that we can see. So what does the moon's gravity do to affect the Earth? It causes the tides, right? Also, they're doing scientific studies that when there is a full moon out, people get to acting a little weird. Many of you noticed that? You've all heard of that before? That sometimes on a full moon, a lot of weird things happen. You tend to get more shootings, more stabbings, more weird things like that happening on a full moon than any other time. Why? Well, no one knows for sure, but what's your body made out of? Most of your body is what substance? Water. What? Water. If the moon can pull all the water out of the ocean, why can't it pull on the water in your body? They are actually doing scientific research to find out if there is a correlation between the full moon and weird things. Or do people just say, well, no wonder we're having weird things. There's a full moon. And they don't notice them on other days. Well, there may be some psychological reason why people act weird or weird things happen when there's a full moon. Because if you're mostly water, the moon can pull on you too. Okay, who's the first guy who discovered gravity? Pardon me, who is the guy who first discovered gravity? Not discovered it, I mean, it's been around forever, but first gave it a title, first did some experimentation with it. Does anybody know? Galileo. Galileo, okay, now how did he discover it? Famous story of doing what? Falling objects? Okay, something fell, what fell? An apple. An apple fell, and he said, this is really strange. Why doesn't this float up? And so he started doing a lot of study. Now, if I took a baseball and a bowling ball and dropped one of them off of Burke High, which one would hit the ground first? Both would. They would both hit the ground at the same time, but the bowling ball weighs so much more. I mean, you're right, but does it make sense? No, it doesn't. I agree. Now, if I dropped a baseball and a feather, which one would hit the ground first? Baseball. Why? Because it takes up more room and has more mass. Okay, a bowling ball has more mass. Why? How could a bowling ball and a baseball, a bowling ball is heavier than a baseball, so how could they hit at the same time? because the pull of gravity on all objects is equal. The only thing that makes the feather fall less rapidly than the baseball is, anybody know? Air resistance. Remember, it is trying to pass through the air. The air is pushing up on it, the molecules in the air. So the feather falls slower. But other than that, if it doesn't reach its so-called terminal velocity, I believe we get to that in a later section. Let me double check. Yeah, so if it doesn't reach its terminal velocity, then it's going to keep falling at the same rate. Now, when they landed on the moon in 1969, is that the year we landed on the moon? Isn't that terrible? I can't remember. Oh, whatever. Okay. As they landed on the moon, they did this experiment. Because there is a vacuum in outer space, there is no air resistance. So they took a feather, and they took a heavier object, a ball or something, and they dropped them. Guess what? They both hit the ground at the same time. So long as you have no air to push up on it, everything is going to fall at the same rate. And when we get into the section on falling objects, we'll talk about terminal velocity. Now, terminal means what? If you have a terminal illness, we're going to do what? It's going to do what? What did you say? No. A terminal illness will do what? It will kill you. It is the end. If you go to the airport terminal, that's one end of your journey. On your journey. And when you arrive at the other terminal, it means it's the other end of your journey. So terminal means end. Terminal velocity means the final velocity that you can reach, but that's due to air resistance. That's why skydivers can do their free falls. Okay, because eventually, very quickly, they reach their terminal velocity and they don't fall any faster. They just float around until the parachute's open. But that's another story. All right, we'll save that for a couple more sections. So this section talks about gravity. The important thing to remember is that mass doubles the force, that if mass doubles, the force of gravity doubles. If the distance doubles, the force of gravity decreases by 1/4, or a factor of 4. Those are the big things to remember about gravity. Okay, we're going to do something a little bit different today. I'm going to give you the worksheet, and you have questions. I want you to do those first. When you finish that, we're going to start on the packet that I have about graphing. And part of that packet, you have a worksheet. And when you finish that worksheet, then you'll read a little bit more and then do another worksheet. If you'll notice on the syllabus tomorrow, it says continue graphing worksheets. Thursday, it says continue graphing worksheets. I expect that by Friday, you should have at least most of those done. Yeah, I expect by Friday you should have at least, well, we may have more, but you should have at least 6 of those worksheets done, which means you need to use your spare time to do some of these worksheets. And then we'll do those for the next 2 or 3 weeks. I believe there are 19 of them, 19 worksheets in the series about graphing. Okay, so first of all, I want you to do the work for today, the worksheet and the questions, which is questions 1 to 4. And then I'll have another thing set out up here for you.